All right, here we go. Electromotive force. Um, so the objective for today, I'm going to switch over just for a second to show you the objective C.2.B1 and 2, which is, which are these ones right here. Right, so students should understand the properties of ideal and real batteries so they can calculate the terminal voltage of a battery of specified EMF, and that's electromotive force, and internal resistance from which a known current is flowing, and calculate the rate at which a battery is supplying energy to a circuit. Well, we're gonna, that second part you'll get to in a problem. We're gonna mostly talk about number one there today. What is EMF and how is it different from just the delta V across a battery in a circuit? All right, so back to the paper. Okay, here we go. Electromotive force. So electromotive force is just the potential difference across a battery's terminals, right? If in any circuit, right, the EMF is going to be the potential across a battery's terminals, but when there's no current. All right, so even so, if basically what you would get putting a voltmeter across a battery when it's not connected to a circuit that's running when there's no current, and it's going to be different than the potential difference if you put a voltmeter across a battery when there is a current running, and we'll see why in a second. But importantly, it's called electromotive force, EMF. This kind of script E is the symbol that we use for it. You would think, since it's named electromotive force, that it would be a force, but it is not. Definitely not a force, right? It has units of volts. Right. So it's just a kind of a historical naming convention. I mean, the potential is, it's called a force because, the potential is kind of what drives the current. Right, the potential from the battery is what drives the current in the circuit. So there's some reason to think it's kind of like a force, but it's not in newtons, it's in volts. So it's a dumb name, but it is what it is. Kind of like how we also know G-force, right? G-force also not a force, right? That's your gravitational field strength, right? It's an acceleration. So we got to be a little bit careful. But that's all. I just got to know it's not a force, it's a potential difference. Why is it different than delta V? Right? And the reason it's going to be different than delta V, the reason you're going to measure a different voltage when there's current flowing through the circuit as when there's not current flowing through the circuit, is because real batteries, as opposed to ideal batteries, which we kind of use in our problems so far, real batteries have internal resistance. All right. Really, you can think of a real battery as an ideal battery, basically what we've been working with, where it's just a delta V across it that doesn't change. An ideal battery and a resistor connected in series. So here's a circuit diagram. Put my paper up. This is the way. All right. All right. Anyway, so here's a circuit diagram, right? And the dotted line here is encompassing just the battery in the circuit. Right, outside here we'd have another circuit, right? A couple of resistors or light bulbs or capacitor if you want, right? But all we have here is just the battery part, and what it is this is an ideal battery here that's got a delta V, and then we usually use lowercase r when we're talking about the internal resistance from a battery. Instead, usually a capital R when we're talking about a resistor that we connect to the circuit, lowercase for the internal resistance. So if we look at these 2 points A, B, and C here, the electromotive force, given what we've just learned, is the potential between which two of those points? Any guesses? Out of those 3 points, A, B, and C, if I want to, and in the real battery, you can't do that, right? You can't stick a voltmeter inside, right? We can really only measure in a real battery outside. But if we could, which 2 points here do you think the EMF gives you the potential between?
A and B, or B and C?
I think it would be A and B.
Really, it's the potential between these 2 points, A and B.
So wait, so you're asking which one would the EMF be equal to the actual potential without the resistance?
Right. These 2 points, A and B. Because you know that if you measure the potential difference across here, you're kind of ignoring the internal resistance. Okay. Whereas delta V, what you actually measure when you measure a circuit that's operating,
Can you hear us, mister?
Yeah, I don't think
that's the potential difference between points A and C, right? It includes the internal resistor. Really, you can't get a measurement of just between A and B, but you can go from A to C. So A and C. All right. The only other thing to really note is that sometimes, so if you're going to be building your circuits, am I missing chat? Oh, that's right. I can't hear you. I had my
yeah.
Oh, there
Mark and Harris are trying to answer you guys or answer you.
Thank you. Yeah.
No problem, mister. It's okay.
No worries, bro.
This is my speaker, so I'll probably be able to hear you on the video recording and just be talking over you. But
oh, it's okay. No problem.
Right. So yeah, okay. Did anybody have any comments that they want to repeat again or questions? Sorry that I had my speaker volume down.
I think Harris and I said A and B as well.
Okay. Good. Yeah. So that's good. Yeah. Usually I should realize when I don't hear anything from you guys that oh boy, that my speaker's down.
Happens, sir. No problem.
No problem. All right. The only other thing to go over then is, so when you're building a circuit, when you're building your circuits, if you're going to be doing it remotely, you're going to be using batteries, and I'll remind you again, but I am going to need. I think the thing to do is if you're not going to be coming in hybrid, if you can provide some D batteries for yourself, I'm going to have I'm going to try to do that by the end of this week, have for you to come and pick up the breadboard, some resistors, some LED bulbs, some capacitors as well. Enough to do the circuits that we can do, that we're going to do in here. But I don't have D batteries to provide to you. If cost is an issue for D batteries, let me know and we can work something out. But I hope that for remote people, if you can provide some D batteries, I don't know how many you'll go through, probably 2 or 3, maybe. It depends on how good you are at not building short circuits and just draining the battery immediately. But anyway, we'll talk about that later. Back to the lecture. We're almost done. So the only other thing to note is that we have, when you're building a circuit in the classroom here, we're going to be using one of these. This is not a great image of it, but this is a regulated power supply. And what this does is we turn these knobs here and we can have it output whatever voltage that we want. Whatever voltage that we want. Excuse me one second. And it acts like an ideal battery because the electricity, it's going to self-regulate. So the DC power supplies that we're going to be using in the building are self-regulating. They act as ideal batteries. The D batteries and the batteries we connect to are going to be real batteries, and they have internal resistance. So any last questions before I pause or stop recording the lecture for today about this EMF stuff? Okay, sounds no. I think I still have my speakers up. So, all right, I'm gonna pause that for there, and let me.